If you could drain the Grand Canal and peel back the mud beneath it, you'd uncover an entire forest. Millions of short tree trunks carry Venice's palaces, churches, and stone bridges. Workers hammered them into the lagoon floor by hand. They have remained down there for more than 1,000 years. Those ancient foundations still carry the city's weight, but something else is sinking the city day by day. And if the buried timber still works, what exactly is then causing Venice to sink, and how in first place they build this entire city on lagoon mud? Well, to understand why anyone tried building here, we have to rewind the map to northern Italy during the 5th and 6th centuries. As invasions spread across the mainland, families escaped toward the Venetian lagoon. A lot of them ended up on islands around Torcello and Malamocco, where some of the lagoon's earliest settlements began. Another community grew around a group of muddy islands called Rivo Alto. Over time, that name became Rialto. These settlers chose the lagoon for protection. Shallow water surrounded the islands, and the channels constantly shifted through soft mud. Large armies couldn't move horses, carts, or heavy equipment through that terrain easily, so the settlers mostly started on natural islands that already existed inside the lagoon. They brought in extra soil and expanded the muddy edges. Wooden barriers stopped that new material from washing away. Natural tidal channels ran between the islands. Venetians widened and reshaped those waterways until they became the canals that still divide the city today. That gave them space for a settlement. Heavy stone buildings created a much harder problem. The upper ground could barely support their weight, and if we cut through one of those islands and look beneath it, at the top, you'll see artificial fill. Venetians added this soil while enlarging the islands and raising their streets over centuries. Keep moving downward, and that fill gives way to soft silt mixed with waterlogged clay. A heavy stone wall would press into this material and slowly push water out of it. One section could settle faster, cracking the building above. Around 4 to 5 meters below the surface, you reach a tougher clay layer called Coranto. Geological pressure had already compressed this clay, and the layer usually measured between 1 and 3 meters thick. But Coranto couldn't carry an entire palace by itself. Many Venetian piles also measured less than 3.5 meters, which meant they didn't all reach that deeper layer. So builders packed short wooden piles extremely close together beneath each wall. The wet soil gripped the sides of every trunk. As more piles entered the same small area, they compressed and stiffened the shallow ground. Wooden platforms above them spread the building's weight across the whole group, which reduced uneven settlement. Now we know what the foundation needed to do. The next challenge was installing thousands of these piles with medieval tools. Installing those piles started with a small patch of dry ground. Workers enclosed the building's footprint with a wall of wooden sheet piles. Venetians called this enclosure. Crews drained the water trapped inside, then removed the loose mud covering the foundation area. Meanwhile, timber traveled toward Venice from alpine forests such as Cadore. Workers tied the wand trunks into rafts and floated them down nearby rivers. Builders chose different wood for different jobs. They used alder, larch, elm, pine, and oak, depending on the weight of the structure and what they could transport. Venetians called the pile-driving workers battipali, which basically means pile hitters. They repeatedly hammered each sharpened trunk into the mud by hand. The crews even sang together to keep every strike in rhythm. Most piles measured between 10 and 25 centimeters across and reached up to about 3.5 meters long. The battipali started around the edge of the foundation and gradually moved toward the center. In some places, they squeezed around 9 piles into a single square meter. They kept hammering until the soil stopped the timber from moving farther. Workers then sawed every pile head to the same height below the waterline. That created a flat wooden base beneath the mud. The builders now had thousands of separate trunks sticking out of the ground. They still needed to connect them before adding any walls. Workers laid thick wooden boards called zatteroni across the leveled pile heads. Some foundations used crossing beams called mattieri. These pieces tied the pile group together and created one wide platform. Crews placed stone blocks over that timber base. Bricklayers could then begin raising the building above it. Near the waterline, builders added Istrian stone, brought across the Adriatic. This dense limestone absorbed far less lagoon water than ordinary brick, so it protected the lower walls from constant saltwater contact. They kept marble and other decorative stone farther up the building, where the tide couldn't reach them as often. Venetians repeated this method beneath houses and heavy bell towers. The Rialto Bridge alone rests on thousands of wooden piles. So now we have timber buried under mud, trapped below the waterline for centuries. Why hasn't it rotted away way. If we zoom into one of those buried piles, oxygen barely reaches the mud around it. That prevents fungi and insects from destroying the pine timber the way they would above ground. Anaerobic bacteria can survive down there, and they slowly eat into the wood's cell walls. But this process takes centuries. As those cells weaken, water fills the empty spaces. The surrounding mud also squeezes the pile from every direction, helping it keep its original shape under pressure. People often say Venice's piles petrified and turned into stone. That's not quite what happened. They're still wood. The foundation works because the waterlogged soil locks the timber tightly in place. The lower brick walls face a different problem. Salt water climbs through tiny pores inside the brick. When that moisture evaporates, it leaves salt crystals behind. Those crystals grow and eventually crack the masonry. That's why builders place dense Istrian stone near the waterline. It slows the moisture before it reaches the brick above, so the wooden foundation can keep working while the ground surrounding it gradually moves downward. Now widen that underground view until we can see an entire Venetian island. The weight of its streets and buildings presses down on layers of soft, waterlogged sediment. That pressure slowly forces water out from the tiny spaces between the clay particles. As the water escapes, those particles move closer together. The soil loses a little height, and everything resting on it moves downward. Regional tectonic movement beneath the northern Adriatic lowers parts of the lagoon as well. Satellites now measure an average subsidence of around 1 to 2 millimeters each year in Venice, although some areas move faster than others. The Freri Church bell tower shows what that pressure can do over centuries. Venetian builders completed it around 1440, and researchers estimate that it continues settling by roughly 1 millimeter each year. Altogether, it has moved downward by around 60 centimeters. And during the 20th century, people made that movement much worse. Jump across the lagoon to Porto Marghera in the 1950s and 1960s. Factories needed fresh water, so they pumped huge amounts from deep aquifers beneath the area. As the water pressure dropped, the fine sediment underground compressed. Venice started sinking much faster. During 1968 and 1969, measurements reached around 14 millimeters in a single year. That's roughly 10 times the rate Venice experiences today. Authorities restricted the pumping around the beginning of the 1970s, and the rapid sinking slowed. The ground didn't spring back. Across the 20th century, Venice lost roughly 12 centimeters of height. Then the water around it rose too, put a marker on the base of a Venetian palace. Now moved the building down by 12 centimeters. During the same century, raised the sea by another smon. The waterline ends up roughly 23 centimeters closer to the doorway. On November 4th, 1966, strong winds pushed an extreme tide into the lagoon. The water reached 194 centimeters above the local reference level and flooded almost the entire city. Another tide reached 187 centimeters on November 12, 2019. Tourism and large ships cause other damage around Venice, but they don't explain the citywide sinking. To control those extreme tides, Italy built moats. Construction started in 2003. Engineers placed 78 hollow steel gates across the lagoon entrances. Lido received 2 rows. Malamocco and Chioggia each got 1. On a normal day, seawater fills the gates and keeps them flat inside concrete housings on the Pun seabed. When a dangerous tide approaches, compressors pump air into them. The air pushes the water out, and the gates float upward on giant hinges. Around 30 minutes later, 4 steel barriers separate the lagoon from the Adriatic. Moats protected Venice during a high tide for the first time on October 3, 2020. It can block incoming seawater for a few hours. It can't lift the ground beneath the city, and as sea levels rise, Venice will need to close the gates more often, disrupting the water and sediment that naturally move through the lagoon. So the next time you see a gondola moving through the Grand Canal, remember there's an entire forest buried beneath it, still carrying Venice after more than 1,000 years. Now engineers have to protect that city, while the gap between its streets and the Adriatic keeps short. If you came for Venice and somehow ended up 5 meters underground counting wooden piles, you're definitely in the right place. Subscribe to the channel because we dig into the world's wildest mega builds projects. Make sure to check the previous videos too.